So next up on our agenda is Hans Koenigsmann. And if we can bring up his introductory slide.
All right, good morning.
All right. Dr. Hans Koenigsmann joined the SpaceX team as the fourth technical member in 2002 and developed the avionics, guidance and control, and software departments as the vice president of avionics. He designed the avionics system of Falcon 1 and supported the early launches as launch chief engineer. He moved into this operational role for Falcon 9 and Dragon and became the vice president of flight reliability, formerly mission assurance. Being responsible to flight risk and safety, he and his team also resolved critical anomalies. With the addition of build reliability, he was also responsible for production quality. His responsibilities also included change engineering, process development, and the quality system. He and his team supported more than 100 launches with thorough reviews prior and flight data reviews post-flight, feeding back the lessons learned, preventing mission failures, and improving both production and operation is the top priority for him. Hans retired from SpaceX in late 2021 after more than 19 years. He holds a master's from the Technical University of Berlin and a PhD from the University of Bremen in Germany. Hans, thank you so much for being here. Welcome to the Flight Software Workshop, and it's all yours.
All right, thank you, and good morning. And I'm glad we fixed the issues we had earlier with the sign up, with the dial-up rather. Anyways, I'm not a software engineer. We can go to the next slide. I was hired as one of the really early engineers within SpaceX, and I ran the avionics department early on, and avionics included actually software and flight software specifically, and guidance and control, and also flight safety. So avionics was a rather broad area at SpaceX, still is. And it actually was a good fit for me because my knowledge is rather broad and not very deep. So you will find that out when you ask probably more specific questions. Anyways, I worked hands-on with Falcon 1 and Falcon 9 specifically. I worked more on the rocket side than on the Dragon side, but I was involved a little bit with Dragon. And then, of course, you know, when it became by the time it became Crew Dragon, I was in the more general departments of build and flight reliability. But early on, what happened is actually I got interested in how to actually make it work. And I ended up with the job of a launch chief engineer. And the launch chief engineer is basically responsible for the risk and that everything goes well on day of launch. And so this over time became my role. The vice president of build and flight reliability, that basically is kind of like the one level above the launch chief engineer, who runs the launch chief engineers and also takes care of the production issues, as Chris said earlier. I did that for many years until recently. I retired in end of September last year, and I'm not affiliated with SpaceX anymore. I still say we and SpaceX in a way that is similar to like when I worked there. So you gotta just remember I'm not at SpaceX anymore. But I do care in general about lessons learned. I want to make sure that we don't repeat mistakes in particular. I want to generally prevent mission failures and improve production operation. A mission failure is not just bad for the company or the organization that has experienced the failure, but it's also just in general bad because there's always a response that is affecting other companies, not just because they have common hardware and software, but also just in general. The concerns just are directed basically at what you learned in the last couple of years. And then obviously, if you have a certain specific failure, then everybody else will be investigated and make sure that they don't have a similar failure. So anyways, the more successful we are as one company or one organization has repercussions on the entire industry. Next slide, please. Okay, those not familiar with SpaceX, this is just a poorly formatted overview of what happened and how fast it happened. We launched the first successful Falcon run in 2008, end of 2008, But prior to that, there were 3 launches that did fail. And I think the first one was 2006. So it took a while to get going successfully. But then once that happened, pretty quickly, SpaceX stepped up to Falcon 9. That actually worked on the first attempt. And then 2012, we were successful in getting Dragon to the ISS and docking, and this whole thing was autonomous with obviously a whole ton of software too. And then on top of that, we actually, Dragon was at that time, it was uncrewed. It was just a cargo version. And then in 2014, we got a contract to convert this, or to upgrade, convert, and have a new version rather, into a Crew Dragon version. And yeah, in parallel, we developed the reusability, which is crucial, obviously, for cost and to some extent also reliability. In 2015, we landed the first booster. I think the first landing that was successful was on land, and it was December in 2015, an OPCOM mission actually. It took us a while, but then we started actually reusing them again. And that by now is actually the way most of the boosters are being used. They fly, they land, and then we actually inspect them and do a little bit of maintenance, less and less as time goes on, and then we fly them again. And it's a thing that actually works really, really well. 2018, we added Falcon Heavy flight, actually just yesterday, 4 years ago. Can't believe it's just been 4 years. It feels so much longer. Then we added autonomous docking, which is required for the Crew Dragon. And then from then on, the first were so fast that I just added them at the bottom there. We started reusing the payload fairings. We became, with Starlink, the largest satellite constellation operator. I guess it does help if you just launch 60 or 45, depending on what version it is, satellites every time. And then in May 2020, we actually, right in the middle of the pandemic, we became the first private company to send humans to the space station, which for me was an absolute highlight. And later that year, we also had the first operational crew launch. And then particularly exciting for me too was the first commercial crew, Inspiration 4, just last month, and basically the last thing that I was very much involved in. So that basically describes SpaceX in the last 19 years, and gives you an overview of what we did. As you can imagine, there was a lot of software obviously involved along the way. I believe there's probably elements that go all the way through those 19 years and have some commonality. My job, as I said earlier, was not to be directly involved in the software, but mostly to make sure that the software works as well as it actually over all of the years worked. Let's go to the next slide. Yeah, I want to go back a little bit to myself. I'm half mechanical, half electrical, and obviously there's no software element in here, but I did started programming in college. Well, at that time, it's going to date me. Yeah, the Atari is going to date me, and the Pascal and Fortran is going to date me. But I did write a lot of software in C and C++, and I'm actually learning Python right now. It's a lot of fun. And I started out primarily because I was interested in integrating equations of motions and to show it on units here. And I was fascinated by nutation and simulation of momentum exchange. And these are technical terms, right? Nutation is the little motion that you really want to avoid in spacecraft. And then momentum exchange is mostly a thing for spacecraft that have wheels and use the gyroscopic effects basically for stabilization, and when you spin up and down the wheel, then things happen. And it's something you cannot show easily on Earth, because gravity is always mixing things up, and gravity is also disturbing your subtle motion. And so what you do is you go and simulate it. And so that's how I basically stumbled into the whole thing and stumbled into the world of simulation. And then when you actually, another thing that happened along the way, it wasn't really planned, but you have a satellite, and then you go figure, and well, how do we test that, right? And then the obvious answer is, well, maybe you can wrap like a loop around it and pretend to it that it's in space, and then see what it does, right? And that's what a hardware in the loop, and to some extent also a software in the loop is. The difference between those two is hardware in the loop, obviously you have the hardware of the satellite, and you feed it information, and you take information from it. In the software, you virtualize the whole thing, and you write one big simulation that also simulates the spacecraft, and you're trying to find out how it behaves. And there's special rules that should go with software in the loop versus hardware in the loop. Yeah, along the way, I found that you can create environments, in particular space environments, that allow you to test things well, they allow you to make tests that you can either simulate ahead of time, so you can test your software before your hardware is done, or you can test your software in an environment that you are not in yet and you will be in at one point in time. And that is just super duper important. Yeah, I think there's going to be comments on the Atari. I did put a picture in there because I actually made the first version of a simulator called AtSim on an Atari, and it was a unit. I plotted a unit sphere on the screen, and it actually did work. So it barely worked, I would say. Next slide, please. Yeah, going back to SpaceX. Falcon 1 had 3 failures, as I said earlier, during its early development, and they were caused by a variety of engineering and operation issues. Just off the top of my head, the first failure was a leaky fuel line, and it really tragically set the engine on fire, and fire where fire does not belong, and so it flew half a minute, and then it came down again, and it was crushing at the time, but it was actually a good lesson learned, and we drew lessons out of that were really good going forward. This is also pretty well described in the book Liftoff by Eric Berger, and the thing that I just described, the burning engine at liftoff, that actually is a picture on the book. If you look very closely, you can see a little bit of fire where it doesn't belong. But anyways, had nothing to do with software, right? There was a little bit of software repercussions on that, because we developed systems where we thought, well, maybe we can find leaks earlier, and maybe we can actually do this in the last seconds. And humans are typically not that good in finding these things that quickly. I mean, that's really great operators, and they find a lot of stuff. But if you actually wrap a little bit of software around it, your odds of finding things that you don't expect are way higher, and that's actually what happened too. Second failure was a problem with the sloshing and the control system, and I was, I felt at least very responsible for that. But also very little software involved, and although the fix obviously affected the software quite a bit, it was a guidance and control, I guess, design issue in that sense. This flight actually went pretty far. First stage was successful, separation was successful. Second stage, was successful for many minutes before it started spinning up, and then the fuel just separated, and it didn't get to orbit. But it did a lot of things that proved that we were right and we did the right thing, and it was great. And then the third flight was actually, well, now it was a new engine, different engine, and well, I'm just trying to describe this a little bit. We went from an ablative engine to a regeneratively cooled engine, and there's differences in how these engines turn off. But we didn't change the software configuration, and I'm careful enough to say configuration here and not software. And in the previous flights, we basically we flew the vehicle. The first stage went out. We pushed a little bit, and then we separated. And the time between shutdown and space separation is really it's critical, because the longer you wait, you're drifting ballistically, and you're at whatever you're still in thin atmosphere basically by the time of the first stage burnout. And the more time you spend without thrust is not good. It goes into gravity losses. It goes, you lose a little bit of drag, and so you want to be quick, right? And so shutdowns, purge, and go. Well, in this case in particular, with a different engine, we basically separated the stages, and then we re-ended the second stage with the first stage, because that particular new engine needed more time for the thrust to die out. And this is also very subtle in one sense, because you can't see this on the test stand. On the test stand, you have this problem that you have a lot of thrust, and then you're not trying to detect very little thrust, and that's not easy. And that's basically what happened here. And so this was the third flight. There was a lot of drama around it too. Elon at the time said he's in for 3 flights. And so I was really worried. After the third flight, the team was pretty down. After the third flight too, it felt a little bit like we didn't even get further than the second flight. We actually got shorter, right? But it also was a little bit misleading, because the fix here was super easy. We actually literally fixed it. It was one number in the configuration that we fixed and sort of in the software. And we added 4 seconds of time between shutdown and the stage separation, and that completely fixed the problem. Luckily, we had another vehicle built at the time, and we just flew it down to we launched from Kwajalein, which is a little atoll in the Pacific, a pretty safe place to launch new rockets. Not a lot can go wrong. Yeah, I mean, at least in terms of damage and population. And so we flew down there. We had this one change made, and flew it, and it went successful into orbit, which was pretty epic after so many years on working this. And so my best software experience is actually that sometimes you can fix things in software. And when I wrote this title down, it was not meant to be really the way I think most software engineers hate it, when you're in a situation that something weird happened to the avionics system, and then can you fix it in software? And it makes the software engineer roll their eyes, and they go back and actually fix it in software. So yes, you can fix things in software. Next slide, please. Yeah, I had a couple other lessons too, and while I'm not a software engineer, and I don't feel like I can speak a lot to the actual software at SpaceX, I do have a bunch of opinions, mostly based on observations and experience working with a company that started at 0 and is what it is now, prime provider for cargo and astronaut flights. So we were a pretty fast-paced startup, as you could guess, and the thing that really helped us was to have multidisciplinary, diverse teams with a flat hierarchy. And in particular, avionics was really, there was software, there was GNC, there was flight safety, and there was electrical people. And what I did early on is I tried to force communication. And I did this by, for example, making sure that a guidance and control engineer sits with a software engineer. And so the formal way of documenting the guidance and control work and implementing it in software is there too, but there's also these two people or more people basically that sit very close together and can overhear a little bit what they say and find out things that are really, really important when things changed. I had, prior to SpaceX, I had some software experience, and one of them involved changes on the software side that had a dramatic impact on the guidance and control side. If you change the sample time and stuff like that, then obviously your gains change, and that was not communicated, and it was a disaster. So I feel like documentation, I'm still in favor of minimal documentation, but the interfaces have to be really carefully documented, and in particular from going from guidance and control to software and back to guidance and control. That is a very strong connection, and that is something that really needs to be documented formally but brave. I'm also in favor of simple workflows and approval processes. Simple tickets, nothing really too fancy, and I'd rather just put a note in there and say I'm using this for a different reason today, than to have a whole branch of tickets that are different because I have just one application here. So, anyways, the simpler and the more together and the flatter in the hierarchy, the better it is. It was easy at SpaceX in the sense because we were new, and there was a clean sheet of almost everything, design, processes, and so on and so forth. But I actually think you can do that in even in established companies too, because you have like project-oriented teams, and then they can basically mimic the startup situation. Second lesson learned: test over analysis wherever possible. And that's obviously super important. Test over analysis means also that you do a limited analysis. You may actually work on the test and the analysis at the same time, and see if you can test something that you also could analyze later on when things are different. The simulation and hardware in the loop simulation is also a test for me, so I count this totally as a test. Next slide, please. Yeah, rockets and software. We talked a lot of about flight software, but there's actually a difference. There's a difference between the rocket and the spacecraft from the software perspective too, and then it actually goes one step further, right? There's the rocket, and then it's Falcon 9 or Falcon 1, and then there's Dragon, as a spacecraft, autonomous, has a lot of different branches. Software can go different ways, and then last but not least, there's actually then the crew Dragon, and that actually has software with I want to say input from people at the same time, right? So now that is basically, to me, then the highest complexity that you can possibly get. But going back to the software itself can be fairly simple. You can fly a rocket with what I call a camshaft. Yeah, it's a clock basically that has rotates a camshaft, and then it opens certain valves with like pneumatic ports opening and closing, and clearly you also you respond to the quickly changing environment in a rocket. You have to do that, and then obviously you have to be pretty quick to keep your control active, and it's a rather quick control loop. But it is pretty simple. The software does the same thing, or can in a simple implementation. The software can do the same thing every time. And that's pretty easy to test, or relatively easy to test, I would say. Yeah, but then you add things that are adding complexity. You add telemetry to the software. You add video software. You just add switching videos, and then you have different sensors now. You add GPS to it. You add an IMU. And then you add redundancy, and that's when it gets a little bit deeper, because based on redundancy and parts failing, you could go this way or that way. Yeah? I must say, actually, redundancy in rockets, it's rare that things fail in those 10 minutes. Once you qualified your hardware basically and made sure that your hardware in general and the design and from the design perspective is able to sustain the environment and does what it does, the random failures that many people are worried about are actually pretty random, pretty rare. And so you're implementing a lot of software for something that has a low probability of occurring. But there are redundancies that are a little bit different. Like, for example, if you run out of gas here, you can use this gas over there, or you can respond to propellant management in a way that is intelligent. You can say, you can make, and then you also get into reusability and landings, right? So it gets a lot more complicated when you say, okay, I'm going to land on the spot, but if I can't land, I got to find out something else. I got to land somewhere else, right? I want to protect both the ground and if I can, the vehicle. And so it gets a lot more complicated when you get into the later development of reusable vehicles and redundancy and so on and so forth. And then another point that I found really difficult, well, I guess it's just an operational thing, is to review the mission configuration. Every mission has a certain configuration. You go to a certain orbit, you go have a certain sequence and attitude and so on and so forth. And it's the smaller the team is, the easier this is to actually review and make sure that you do the right thing. But when the team gets really big and the missions go quickly, then this is actually a thing that does need attention and it's not that easy. It tends to be difficult to have a larger team review a mission configuration and to make sure that you do have the right configuration. This is something that I always worry about because it has nothing to do with that the software is wrong or right. The software just executes very correctly something that has been input wrong in a certain way, and so that needs to be really carefully treated. Like I say, the software tends to perform relentlessly as instructed. Whenever you have something and the software doesn't do what you expect, it turns out that typically it's the operator or the person who asked the software to do something. And what helps actually is to have more software integrated into the hardware team. Basically, what I'm not saying that the software work itself needs to be integrated, but what I'm saying is to have software knowledge spread around the company into the hardware teams, and so that the hardware team will understand how the software works, and the software teams, there's no way, I mean, the software teams must totally understand how the hardware works. And so the more you can integrate those teams, the better it actually is for both mission reliability and also to some extent efficiency. Next slide, please. Yeah, this is going back to the loop, the hardware and the software loop, and you see a little bit there. My crappy hand drawing spacecraft has an actuator, and it's the actuator responds to some input. In case of a rocket, that's a gimbal angle or a valve that opens or something like that. And then you have a simulator that's a different computer that reads measures this input, and then integrates it, has added complexity too, has done an Earth position, atmosphere, magnetosphere, and all these things. And then the simulator tells the IMU or GPS system on the spacecraft basically where it is and what it's doing. And then the spacecraft responds to that, and it does the right thing. This is a little bit more for a rocket. Actually, it's good that the primary or the important part of the mission is basically 10 minutes or 9 minutes, and you can really do a lot of hard-in-the-loop simulations to test it. Yeah. But for spacecraft, obviously, it's a little bit harder when you have like a 10-year mission. How do you simulate that in hard-in-the-loop simulator? And you basically break it down to certain parts that are relevant and more important, and then let the rest do in a different way. One different way is actually to implement the whole thing in software. And the critical part is to have these two errors, the control output and the control and the environment input, be very distinct, and don't cheat. Don't grab like a variable from the simulator part into the spacecraft, because if you do that, bad things happen later once you actually have the hardware flying and want to test that. So if you're disciplined enough and have a software in the loop simulator, now you can actually do something that you can't do in real life. You can speed it up, and suddenly you can actually have a 1-year mission in possibly a day. And then look at the data and figure out what happens to the spacecraft in long term. There's certain elements that are super important in hardware in the loop, like certain, for example, momentum management is something that is a long and slow process, and so it's hard to calculate. It's hard to accurately calculate, and it's relatively easy to simulate with a software in the loop simulator. So these are not the only tests that you do, obviously, on spacecraft and on rockets, but in combination with like a polarity test, I always consider them the prime tests of the system, where you find out whether the system works or not. And in many cases, I trust these tests more than a thorough review of the source code. And it doesn't mean that you shouldn't do that. I mean, obviously, you should do everything you can. But these tests, for me, they were always like a final bow on the software and the configuration. All right, next slide, please. All right, there's a bad part on being a software engineer, and I hope I'm not. This is probably not news, right? But if you're building up something, then you obviously need to build hardware, and then you need to build avionics, and you need to make software that fits those builds. And so it's really hard to actually be not the latest part here and on the software, because the hardware, as much as you plan for this and as much as you're trying to align this, there's always going to be surprises, and there's always going to be something that makes you go back and change software and fix it in software, so to speak. And so by definition, so avionics was always a little bit late, because you need to know the other systems on the vehicle to respond to that in software, and then your lead times are relatively long in some cases. And then on top of that, you actually need now the software to run this. So it's a difficult process to get this all together in one point prior to a launch, and feel good about the quality of the work, in particular in the last couple of months when everything gets really intense and hardware shows up and has surprises. And then on top of that, like I said earlier, the flight software is hard to test. It's not a lot you can do in a lab without a hardware loop simulator, and now you're fighting over resources. And there's only one hardware in the loop simulator. Maybe there should have been two. And all these things are things that are lessons learned, which, if you do it the first time, it's on one side you have the advantage that everybody knows their system really well. On the other side, you're doing it for the first time, so obviously you're going to make mistakes. And the particular comment here on how to update that actually is when you fly, right? If you fly, if the rocket flies and you find out between stage separation and second stage ignition that you should have updated the software, then it's probably too late. But on the flip side, also there are satellites being launched with basically just an operating system, and you just upload the software later, and take advantage of the time it takes for the spacecraft to get from the final tests to launch, which is typically a couple of weeks, couple of months, depending on who you work for, delay. And so you can actually take advantage of that and continue writing software. But it is a risky way. It's a risky thing, and for most organizations, they choose to leave the software as it is by the time they test it and then fly it as it is. But I just want to point out that some people had been making changes on the software itself on spacecraft. It's not without challenges, like I say. So I'd be super careful, but it's certainly something that on the commercial side gives you some advantage. You might actually test more, test longer. Everybody feels a little bit stressed in terms of the last test prior to launch. If you've done the mission, you probably know very well what I'm talking about. The real technical challenge on a software engineer is actually also that you need to understand the system. You need to understand, how propellant systems work. You need to understand how gas, again, you need to understand the thermodynamics of that to some extent too, right? And so suddenly you need to understand things that you never learned about, or understand guidance and control algorithms and stuff like that. And that's something that obviously I find it exciting. I find it great because I learned something. But it could be a challenge to do and contribute a little bit to stress in an environment, work environment. So and obviously, when there's a bad side, there's also a good side. So next slide, please. Like I said earlier, I'm not a software engineer, flight or ground, but I've actually written a little bit of flight software and many decades ago, and simulation software, and I enjoyed it actually. And I enjoyed it because I'm deep in my heart, I'm a pilot, and the software is in control. The software basically is the pilot. The flight software is what runs the vehicle, and if you wrote the flight software, by extension, you are the pilot, together with guidance, navigation, and control. Which is like maybe the co-pilot or the pilot. It's not totally clear on where the dividing line there is, but in my world, the flight software and the way you configure it for flight had always a pilot-like element. Yeah, it always is the final thing. It's always is the thing that basically makes it fly or not in the last minute. And I think for that reason, I just enjoyed it. It's just like you see the vehicle doing something, and it rotates now, and it goes that way now, and that's because you programmed it. That's because there's something in there that you put it on not on paper, I guess, on a computer, and that's actually what makes it work. So you can have this huge rocket, and it responds to this little number that was put down, weeks ahead of that. And that's pretty satisfying, and that's pretty cool. You can say, okay, I did that as a flight software engineer. And so obviously that is very satisfying. That's part of why I like it too. That's part of why I thought, okay, I can actually do that keynote despite the fact of not having any particular knowledge when it comes to real time or all these special things. I'm pretty bad at that. And then maybe an extension also, when you do build a simulation and you do find out that the equations of motions actually do work, and that your physical understanding is correct, or maybe it does need a correction. Yeah, that is a pretty powerful thing too. That now allows you're simulating a really difficult situation for the spacecraft or for this rocket, and you fly the first time, you realize, oh, it's almost like the simulator. Maybe max Q is a little bit later, maybe it's a little bit earlier, and that's because the atmosphere is a little bit different than the one that you used in your model. But you can go back and actually refine that, and that's what we did. I mean, we refined it to the point of, can we make this a predictor? Can we make this actually something that basically, not just tests the rocket, but also validates it and gives you an idea on how much fuel there's. Can you add a statistical component to it? Can you figure out a little bit on the probabilities on certain things? And there's a lot of things you can do to make this even a tool beyond the pure testing and does this actually work tool. Yeah, there's a lot of stuff you can do with that, and I guess do the impossible basically that you couldn't do otherwise. And then, as I showed on earlier on the Falcon 1 example, there's cases where you can fix things in software, right? Where you actually have one software version or one configuration version, and the version does actually exactly what it was supposed to do, right? It should be really pointed out that when you command the vehicle to separate in a second, and it does that, then that's exactly how the software works, right? But then your requirements change and say, hey, can you change it actually in can you separate it and then start the second stage 5 seconds later or 4 seconds later, I think was the number. Then you can do that and fix it, and that's pretty satisfying too. And it can save the mission, it can save the company, it can save a lot of things. And you did that also with your flight software with a little number that was changed. And I think that's the end of my presentation. I thank you for listening, and I hope you got something out of it and it was entertaining.
Thank you so much, Hans. It looks like we do have some time for questions today, and I'm going down the Q&A list on Zoom, and I see quite a number of them submitted and upvoted. So the first question, could you provide any insight into why Linux with a real-time patch was chosen as the operating system for SpaceX flight software as opposed to a real-time operating system? How did you deal with the non-deterministic effects of Linux while testing and qualifying as Class A software?
Right. I'm actually not totally sure which version and so runs on the flight software there. I do remember we had some early I want to say experiments with real time, and we found that you can I don't want to say, maybe brute force is the wrong word, but you know what I mean, right? You basically just, your computer is fast enough, and the things the operating system does on the side, you can control that to some extent, not totally, but as long as it doesn't go off and what's an update during flight, that's really bad probably, but you can control that. Yeah, we found that it's pretty deterministic in general, and there's another thing to it too, right? Deterministic depends a little bit on your definition and on how deterministic you actually want to be. If something runs at, let's say, 10 hertz, and so it's 100 milliseconds, and you're off by 10 milliseconds in this cycle and 8 milliseconds in the other cycle, a thing like a rocket doesn't really care in many cases on this, as long as the average is okay. I mean, it weighs £1 million or 1.5 million pounds, and it's just such a big thing that typically that millisecond doesn't matter. There's certain things that do matter, like certain latency between data, and so you got to be careful there. But that's partly also why you test it. That's partly why you actually have this hardware in the loop test, and that's partly why you do these elaborate tests and trying to figure out, where are your limits. You can, when you do those tests, you can actually literally just say, okay, how bad can it go, and then move the needle to delay, and then you finally find out, okay, this is the limit. So, and then you measure your real data, and you find out, okay, you're like light years away from your limit, and then it's safe. That's typically how I feel like it's an engineering approach to deal with it. It's and there's enough tests and test data and analysis to make sure this is not critical. There's also always a little bit this discussion about like open source versus proprietary, expensive piece of software. Which one's better? And I don't know. I tend to believe that if 10,000 people use the software every day, or let's say it's 10 million, or actually 100 million, and there's a good feedback system, that is a great thing.
Okay, great. Next question. Where do you think is the biggest opportunity areas for deep learning and AI throughout the launch vehicle verticals, such as design, control, and operations?
Yeah, I think that's probably in the flight data, in the post-flight thing. I don't want to have my rocket learn during flight. That's a terrible thing. In particular, I mean, learning has an element of, I'm trying to try this and see how it goes, right? There's clearly a random poke in the learning process, and that's actually true for almost everything. It's evolution is like that too, right? It has random mutations that die off because they were not good, and then it has like the one that actually is successful, and learning is maybe a little bit more directed than that, but it has an evolutionary element certainly. So During flight, that would be a tough thing to do, unless you really have a specific application, like you're trying to learn like how whatever. If you can use the star picture or something like that, that's a different situation. But like purely the flight software part that I'm concerned about mostly is control and the operational sequence and so on and so forth. There's not a lot there, but then going back to looking at your data and trying to find out, you got this launch and has a certain set of data, and you have that launch and has a different set of data, and you're trying to figure out, is this an indication for a problem, or is this actually just a variation that is normal? And that's, I think, where it can help you. It's hard. The hard part is to understand the system and then to actually figure out something that, and then to feed that information over to the software system. But at the same time, maybe the software system can help you to actually find the details on the system itself.
Okay, great. Next question. SpaceX seems to use multi-core processors on many of their rockets. What type of issues did you run into when trying to test these multi-core systems for flight? Yeah,
that's an answer I actually don't know the answer to, and even if I would probably be a little careful answering that. Yeah, I don't think I have a good answer for that. Sorry.
Okay. Did you automate your hardware in the loop tests to be running constantly? Do you run unit tests on the actual hardware?
I don't think so. And I think partly it's because it becomes such a valuable resource that you want to do specific tests, and you have a list of tests that you need to go through. And so you can do, it's more software in the loop is probably the better thing to automate, because then you control everything, right? You control software, and now you can basically build the code and run an automatic test at the same time and see if you get to orbit or not. But on the hardware is also hardware is always a little bit finicky, and now I'm probably going to get a lot of comments from hardware engineers. And then the hardware in the loop table, which typically, it's basically a rocket, right? Or it's a spacecraft or whatever it is, but it's typically valuable hardware, and the hardware, the loop table doesn't get the prime hardware, the mission gets the prime hardware. And so there's little things that are, in the details that make this a little bit more difficult to really consider the unit test, because I think there's variations in the hardware too. And to be fair, I do want hardware in the loop tests. I want them to have variations. I do want hardware to respond to a little bit different. I also want the timing to be different, because I want to see if the software really responds to these parts, or if it is robust, basically.
Okay. Next question. Your example of solving the rocket problem by adding a 4-second delay via change in a software parameter was interesting. Once the anomaly was understood, were you able to replicate it in simulations?
Yeah. I mean, yeah, totally. Once we understood what the problem is, I mean, it's heartbreaking, right? This is like the third launch, and you now 2008, we were 6 years into this. So for 6 years, you doubt yourself, and so yes, we knew this pretty quickly. This actually is another comment from me. So in the beginning, you have typically anomalies that are quickly resolved. And that's probably not true for everything, but it's design errors. And you look at it and go, I made the wrong assumption here, I did this wrong, or whatever. There's always somebody who can, you can find out why this happened. And I'm not saying wrong in a way that this is a personal thing or not, because you made assumptions, right? And you discuss those within the organization, and then everybody says, yeah, this is a good assumption, we should go with that. And then it turns out this assumption is not correct. It's more subtle than that, but you get the idea. And so I feel like the early things are design failures, and then as you keep flying, it gets more and more complex, and now suddenly you actually run into production issues and little things that affect the qualification of parts. Yeah, and it gets a lot more difficult to resolve anomalies later on than early on. So yes, we knew this pretty quickly.
Okay. Have bunch of questions actually grouped up together. I'll read them off. How do you manage configuration data, like source code configuration management or with other data management tools, such as a relational database? How do you test configuration data changes, and how do you make those changes and guarantee the right data is used? Okay, I'm not super smart at that topic, but it's all source control, basically, whatever SVN or Git. I'm actually not really super sure. I'm just learning again how these systems work. Yeah, but source control in itself is not really the answer. You also need a little bit of like documentation wrapped around it. Why did I make this change? So that you can actually walk it back and figure out. And there's going to be later on. There's going to be an approval to that. Once you hit certain milestones, you don't want people to change something between, let's say, a static on a rocket, a static fire and flight. You want to be super controlled on your changes, and so the good thing on these version controls is they send you emails if somebody messes with it, and then I could rather pick up the phone and say, hey, what's going on here? And then that to me is just the greatest tool in the world. Total control. All right. What frameworks or platforms did you use for performing hardware in the loop tests? I don't think I give anything away if it's probably the same type of system that we use on the flight software, like Linux type thing. And that's actually. Yeah, think about it. I mean, when you run your hardware in the loop simulator in Linux, it's just the obvious answer because that's what software engineers like working with, because nobody else can work with it, and that's part of why I actually like the Macs. Let's say Linux is the obvious choice for programmer, right? So you program your hardware in the loop test in Linux, and then you find out the hardware in the loop system is basically a real-time system, right? And then you get experience with Linux, and then one day you might actually look at that and say, you might just use this on the other side, right? I mean, that's how it can basically, how you can establish a lot of experience, a lot of data with a system that is not really a real time, but pretty real time. Okay. If it is possible, let me just add to this, because the real time thing is really dependent on how what your time constant is, right? If your time constant is in the seconds, it doesn't really matter. But if your time constant is in the milliseconds, you got to be super careful. I just want to add this. Yep. If it is possible to push code fixes to the vehicle in flight, what are the limits of this capability? I.e., can this be done mid-launch or only on orbit? And also, does the flight computer require reboot after the update is pushed? So the rocket has no way to do this, right? I just want to be super clear. I did this. I said this more as a hypothetical thing for let's assume you would launch a system of satellites that has capabilities in the beginning that are just minimal, and then you extend them. So for the system like that, you would want to have the update maybe in flight. And also, like I said, it's a really tricky thing. On a software on a rocket, I was just using that as an example why you wouldn't want to do it, and why it's probably not going to work well. Because if you make a change, I mean, obviously you want to run a hardware loop test after that, right? You want to check out that this actually works, and then you want to review it with your peers, and there's a whole process wrapped around how to make a change on flight software that depends a little bit on what the system is for, but it would be super funny if you could do that in flight and see the responses to that. That's lots of loops probably. I found on the other side, I mean, to try to do an analytic work or programming under the stress of launch is, to me at least, nearly impossible. There are people that are cold-blooded enough to make changes and say, oh yeah, we can make that change here and then it's good to go. But I don't have that capability. I make mistakes when I do that. Okay. Looks like we have time, just a few more minutes for a few more questions. I'd like to remind everybody to please take a look at the Q&A and upvote any questions that you find interesting. That is how I'm sorting through them. So next question is, any comments on error analysis baked into simulations, linear covariance, Monte Carlo, and so forth? Error analysis. Okay. So you can do a lot or you can do a little. And
And this was going to break, some people's heart here, but I found there's very little difference between a lot of analysis and a little analysis on the error side, mostly. There's certain analysis that's super important, like buffet and if you have a configuration that's a little bit unusual, like if you had fins, you got to be careful. If you have new sort of fins, like good fins, then obviously you want to look at that a little bit and not a little bit, a lot, and figure out how they work. And because otherwise otherwise you don't have any data to work with. But in terms of like going all the way back to Falcon 1 and how much error analysis we do, we didn't do a lot. We did a little bit just to get the performance right and to make sure that the system has enough propellant to overcome drag, basically, or the integrated drag. And that's something they need to be careful about, obviously. It still involves complex tools, and it's not something that you could just wing at the end of the day. But it is still not a full 3D analysis and everything. I do want to say if you do more and more analysis, it gets better. And there's certain areas also like venting and other disciplines that are really dependent on good analysis. But just to get it off the ground and into orbit, you can get by with like limited. I would call this limited analysis probably.
Okay. Next question. One of the challenges with using simulation for testing is to have the right balance of reality being simulated while still being able to run meaningful tests. How have you addressed this balance, or when you realized that the simulation was not the right one for the testing in question?
I don't know. I mean, this is kind of engineering judgment, right? There's atmospheric models that are super complex and great, and I would use them for satellites because you don't need an update every cycle. You could just get the atmospheric density and then propagate with that, or basically propagate the equation of motion with that for like a minute. And I don't think the error is very large. You can actually test the error, how big would it be, right? You find it's zero. But when you use that complex software or that complex atmosphere now for a rocket, it's not particularly helpful because the bigger part there is that the atmosphere changes as you go up, just density, and the other impacts like F10.7 or solar activity, AP, and so on and so forth are not really important. So you got to pick and choose a little bit on what you do, right? On a rocket, you go with the simple software. On the atmosphere, that does the overlaying effect, like density change or pressure change, basically very well, and temperature change maybe. And then on the satellite, you really want the more sophisticated that has F10.7 values, because those are effects that you don't see otherwise, right? And then the same is true for like other models. Like, do you need a magnetic magnetosphere model for a rocket? Probably not. But I do want to put it on the spacecraft, and you have magnetic control. So I think it's a pick and choose. And you can always, the really simple thing is to use one model and to use the other model and look at the data if they make a difference. And if you find there's no difference, go with the simple model. In some sense, I always, and that also needs to be really carefully looked at and not just simply implemented. I always like to have a little bit of error in the hardware loop test on the models, because you don't know if the model really is good. So add 10% to the model just arbitrarily and see what it does. Or at 20%, right? Or at 100%. And then see where it actually gets into trouble and play around with it, because the simulator allows you to do this. Reality does not.
Okay, great. And I think we're out of time. So Hans, thank you very much for an excellent presentation and the extended Q&A today. Thank you very much.
All right, well, thank you.